Welcome to this lesson on stellar evolution. Today we'll be learning about the life cycles of stars, from their birth in molecular clouds to their eventual death as white dwarfs, neutron stars, or black holes. Let's start with star birth. Stars are formed in cold, dense molecular clouds in space. These molecular clouds contain mostly hydrogen gas along with some dust and heavier elements. When a region of this cloud becomes dense enough, it begins to collapse under its own gravity. As it collapses, the central region becomes a protostar, a hot, dense core surrounded by a rotating disk of gas and dust. Some material gets ejected along the magnetic poles of the protostar, forming powerful jets that extend outward. These jets help clear away surrounding material. The mass of a newly formed star determines its entire life cycle. Stars can range from about 0.08 times the mass of our Sun up to about 150 times the mass of our Sun stars, with less than about 8 solar masses are considered low-mass stars, while those with more than 8 solar masses are high-mass stars. Objects with less than 0.08 solar masses never get hot enough in their cores to sustain hydrogen fusion. These failed stars are called brown dwarfs. Now, let's focus on the life cycle of a low-mass star like our Sun. A low-mass star spends most of its life on what we call the main sequence, steadily fusing hydrogen into helium in its core. For a star like our Sun, this stable phase lasts about 10 billion years. When the hydrogen in the core is exhausted, the core begins to contract and heat up. This causes the outer layers to expand dramatically, and the star becomes a red giant. At this stage, hydrogen fusion continues in a shell around the helium core. Eventually, the core becomes hot and dense enough for helium fusion to begin, often in a sudden event called a helium flash. This fuses helium into carbon. When a low-mass star, like our Sun, reaches the end of its life, it doesn't have enough mass to fuse elements heavier than helium. The star expels its outer layers into space, creating a beautiful planetary nebula. What remains is the exposed core of the star, a white dwarf. This small, dense, hot object will gradually cool over billions of years. High-mass stars follow a different evolutionary path. A high-mass star burns through its fuel much faster than a low-mass star. It fuses hydrogen into helium primarily through the CNO cycle rather than the proton-proton chain that powers stars like our Sun. After exhausting its core hydrogen, a high-mass star expands into a supergiant, even larger than the red giants formed by low-mass stars. Because of its greater mass and higher core temperature, a high-mass star can fuse elements beyond helium. It undergoes a sequence of fusion processes, creating carbon, oxygen, silicon, and eventually iron in its core. Iron is significant because it marks the end of the energy-producing fusion reactions. Fusing iron actually requires energy rather than releasing it. With no energy generation to counteract gravity, the iron core collapses. This triggers a catastrophic explosion called a supernova, which blasts most of the star's material into space. Depending on the star's initial mass, the leftover core becomes either a neutron star or a black hole. One of the most remarkable aspects of stellar evolution is nucleosynthesis, the creation of elements. The lightest elements, hydrogen and helium, were mostly created in the Big Bang. But stars are responsible for creating nearly all the other elements in the universe. Low-mass stars like our Sun can produce elements up to carbon and oxygen through fusion. High-mass stars can produce elements up to iron in their cores through fusion. The extreme conditions during a supernova explosion can forge elements heavier than iron, including gold, silver, uranium, and many other heavy elements. When stars eject material, either through planetary nebulae or supernovae, these elements are released into space, eventually becoming part of new stars, planets, and even living organisms like us. This is what Carl Sagan meant when he said, "We are made of star stuff." Finally, let's briefly talk about binary star systems. Many stars in our galaxy exist in pairs or multiple systems, orbiting around their common center of mass. When stars in a close binary system evolve, they can interact in fascinating ways. For example, when one star expands into a giant, it may transfer mass to its companion. This mass transfer can lead to spectacular events. If a white dwarf accretes enough matter from its companion, it can trigger a runaway nuclear reaction and explode as a Type Ia supernova. Understanding stellar evolution helps us trace the origin of elements in our universe and provides insights into the past and future of our own Sunday, from the birth of stars in molecular clouds to their eventual death. And the recycling of their material, stars are the engines that drive cosmic chemical evolution. Thank you for joining me on this journey through stellar evolution. The next time you look up at the stars, remember that you're witnessing the universe's element factories at work, creating the building blocks that make up our world and everything in it.